What's up everyone, welcome back. In this video, we're going to prove that there exists infinitely many positive integers n that satisfy for n squared plus 1 is a multiple of 65. How do we do it? Let's pause the video and try yourself first. Are you ready? Here we go. So in order to prove that this expression is equal to 65, it's a multiple of 65, we're going to prove it in the following way. By the basic idea in number theory, if a number is divisible by another number n, then it must be divisible by the prime factors of n. So what will be a prime factors of 65? It will be 5 and 13 respectively. Then in this case, it is sufficient for us to prove that the expression 4n squared plus 1 is a multiple of 5 and a multiple of 13 at the same time. So how can we prove each case? Well, let's start with the easier one, when the expression is a multiple of 5. In order to prove that, we want to think it in the following way. What would be the possible n values that we could have such that the expression will be a multiple of 5? Well, we can just take the modulo of 5 and make a list that if n is having a remainder of 0, 1, 2, 3, and 4 respectively after divided by 5, what would n squared be? And then later on, we will also conclude what happened to the expression of 4n squared plus 1. So in this case, when n is equal to 0, of course, n squared is equal to 0, implying that 4n squared plus 1 is equal to 1. And when n is equal to 1, n squared is equal to 1, then the expression will be equal to 4 times 1, which is 4 plus 1 equals 0, or having a remainder of 0, meaning that this expression will now be a multiple of 5. Then as we complete the table, we actually can see that in this case, we have only two values that will satisfy, which is when n is congruent to 1 or 4, as known as -1. In mod 5, will actually imply that 4n squared plus 1 is congruent to 0 mod 5. In other words, it will be a multiple of 5. So we now just need to play the same game for the other part when you try to consider it in mod 13. Then if we try to figure it out, we actually will want to show that n squared has to be congruent to 3. Now, how do we see it? We can just set it as an equation. Now, this equation is going to work easily if the modulo that we're taking is a prime number. So in this case, 13 is a prime. So we can just rewrite it as a quadratic equation that 4n squared plus 1 is equal to 0 in mod 13. Then subtract 1 on both sides, we get 4n squared is equal to -1. But again, -1 is just the same as 12 here. And then we can divide by 4 on both sides because we're not dividing by any zero divisor. Again, what is a zero divisor? Go back and check out my other videos where we talk about ring theory and stuff. Okay, so in this case, as we divide by 4, we get the right side is equal to 3. So now we need to consider what would be the possible n such that n squared is equal to 3. But what is 3? 3 in this case is just the same as 16. Because we're in mod 13, we can just add or subtract any number of 13s, and it will still end up with the same result. Therefore, if we look at it, n squared equals to 16, of course, we get n is equal to positive or -4. But what's -4 again? That is just same as adding 13, which is same as 13 minus 4, which is equal to 9. And now we actually end up with the other conclusion that if n is congruent to 4 or 9 in mod 13, we will be able to get that 13 is a divisor of 4n squared plus 1. Finally, we are now going to use the Chinese remainder theorem and say that since 5 and 13 are relatively prime, if we have any solutions for both situations, we can combine them together to be able to list out the possible results of the modulo, the product modulo. So in this case, we can conclude that n will have results in mod 65, and the combination will be using these 4 values to the 2 by 2 combinations to get out the 4 different results. Which would be, let's see, if we set n is equal to 1 mod 5, and let's say n is equal to 4 mod 5 and n is 4 mod 13, clearly 4 is one of the options. Then what else can we get? If we set n is 4 mod 5 and n is 9 mod 13, of course 9 will also be a result, because again 9 is just equivalent to 4 in mod 5. Now to find out the other two, we're going to consider 4 plus 13 times something, and again that is how we found the answers from the Chinese remainder theorem by brute forcing. And then we have few options. We have 4 plus 13 times k, for k is between 0 to 4, and that is because these are the possible values under mod 5 if we consider it as a field. Then if we substitute in exactly one of the values, we'll be able to yield the answer. So we can double check. When k is equal to 0, we have 4, we already included, but we try to get this to be congruent to 1 mod 5. So it doesn't work, and as we keep trying, when we get k is equal to 4, we have 4 times 13 is 52, plus 4 is 56. Again, that will be the same as 1 mod 5. So we found our third answer, and lastly, we add 5 to get 9 plus 13 times 4 is 61, which is congruent to 9 mod 13 as well as 4 mod 5. And that will give us our final answer.